So my name is Csaba Fitzl, and I will talk about finding vulnerabilities in Apple packages at scale. So a few words about myself. I'm currently working as a principal macOS security researcher at Kanji. Kanji is an MDM solution company for Mac devices. And we also have like a security EDR product we are developing. I used to work at Offensive Security, where I wrote a macOS exploitation training, which goes by the EXP312 name. I used to be a red blue teamer. Before that, I do macOS bug hunting, part of the job, and also in my little free time. I'm close to 100 CVs with Apple. I'm married, have 2 kids, and I really like trail running and hiking. So before I start, how many macOS users we have in the room? Okay, pretty decent number. So the agenda is very packed. I will talk first about the Apple security model, how it's different from every other OS you probably know. Then talk about the system install daemon, which is responsible for installing Apple-signed packages. We'll call out a few old vulnerabilities in this space, then talk about the software catalog. How did I use ChatGPT to scale the research? And then finally, we'll talk about 5 different vulnerabilities I found in the packages. And as a closure, I will talk about how Apple mitigates all these problems and why it was hard at the first place. So Apple security model. So macOS and iOS is not your typical OS, like if you think about like Windows and Linux. It does has a POSIX heritage, so it's coming partially from FreeBSD. But it's very, very important that on macOS, root is not equals to God mode. So if any Unix system you are root, you can do anything on that system. On macOS, this is far from being root. Root is really like an admin user with more privileges, but it cannot do everything. And on macOS, we have quite a few layers of security, like the sandbox, TCC, which is the privacy framework, all those annoying pop-ups, like this application wants to access your microphone, your camera, whatever. This is all TCC. We have SIP, which stands for System Integrity Protection, also called as rootless. I will talk about this in a little bit more detail in a second. And on macOS, we have a lot of security boundaries. Like if you think of Windows, there is a single security boundary going from standard user to admin, and basically from low admin to high admin to system to kernel. According to Microsoft, there is no security boundary in that space. So if you are admin, you can get kernel code execution by design. On macOS, you can go from normal user to an admin user, that's a boundary. You can go from admin to root, that's a boundary. And you can go from root to kernel, that's a boundary. And we also have entitlements, which makes it even more granular. And process injection is generally not allowed on macOS, even between processes that run under the same privilege level, like under the same user. In the heart of macOS security and iOS, it's code signing, basically. On macOS, it's not mandatory. On iOS, it is. Although on Apple Silicon, you have to at least ad hoc sign, basically sign it without a certificate, your application. The root of trust is Apple. Developer certificates are issued by Apple, and that's how we get the chain of trust. And the code signature can contain entitlements. Now, entitlements, they are like strings in the code signature that gives you very, very specific rights that you can do X. So most of these entitlements, so some of them are usable for by developers, but most of them are private to Apple. And you cannot add those private entitlements to your code signature because the system will refuse running that process or application if you try to basically possess an Apple private entitlement. But these entitlements can give you privilege like this process can talk to that process. Or you are allowed to write to location X and only to that location. Maybe you can install a kernel driver. These are all controlled through entitlements. So we can see that even if you are root and you don't have any of these entitlements, it's very limited what you can do. And if you get access to some entitlements, it will give you access to something very specific. So the security model is really granular. We have system integrity protection, also known as rootless. It's basically a global sandbox applicable for all of the processes on macOS. The main goal originally was to basically protect core system resources. So, for example, all the core system files which are building up the operating system are not modifiable by anyone, even root. Some entitlements can give you a bypass to some parts, but in general, everything is protected. We have a more traditional sandbox, like the application sandbox. It's basically all of the applications are containerized, so they are running inside their container, and they can only access one very specific locations, and basically that's it. We have TCC, as I mentioned, that's the privacy framework. So Apple considers many resources as privacy related. So for example, your desktop, your documents, your downloads, your microphone, your camera. There are, I think, more than 20 categories or around 20 categories right now. Again, these are the annoying pop-ups you get that, hey, this application wants to do this. Do you allow it? And if you don't allow it, like even if I'm root and the user denies accessing the microphone, you cannot access the microphone with an application. So that's briefly how the security works on macOS. And let's jump into system install-D. So system install-D is a root daemon which is responsible for installing Apple sign packages. And when I say Apple sign packages, it means the package is signed by Apple directly. So it's not like I have a developer certificate from Apple and I sign it. That's a developer signed package. Here we specifically mean the Apple sign packages. So basically, and these packages are like Apple software that you can download from Apple. Now, this daemon has quite a few entitlements, as we can see. Again, these are strings. And at the very end, there is a very powerful one, which is called com apple rootless install heritable. So it basically allows it to modify system integrity protection protected files. And the heritable part means that if this daemon spawns a process, that process will inherit this specific right. So basically, if the installer spawns a shell, because it has to run a shell script, then that shell script will have access to these zip protected locations. That brings us into packages. So packages are usually built up in two main parts, simplified. Basically, they have the files that will be placed on the operating system in a specific location, and they can also contain pre- and post-installation script. So, for example, a pre-installation script can contain like stop the application if it's already installed, delete it, then install the new one, and maybe back up some application data related to the application, whatever you can think of. So these are the two main parts. So when we try to exploit system install D, we will try to exploit these installation scripts. So how we weaponize what our exploit, what will be the main goal to achieve. So I targeted a property list file, which is a configuration file on macOS called the Hello Application List plist. It's basically a TCC, a privacy database, which can contain information which application can access which private resource. So normally it's contained in a TCC database, which is a SQLite database, but this is like an extra property list file you could use. This was removed on the latest macOS version, so it was up to macOS Sonoma. But so our target for the exploitation will be this plist file, and we will want to add an entry. Typically, I want to add like my terminal. I will give it full disk access, which means it can access all of the private resources on the system. So it's a very powerful right. So a few notes about past vulnerabilities. Back in 2019, Jerome Bradley found a very simple vulnerability. When you install the package, he could swap the package during the installation, place his own package with his own script, so he could just do any custom code execution by swapping the package. Later on, there was another one where the install script executed the binary, which you had control over. So basically, you could override that binary, place your own, and you got code execution. Then there was 2021, it was called Rootless by Jonathan Bar-Orr from Microsoft. He found that if he modifies the etc.env file, it's consumed by the Z shell application, and he can run custom commands out of that environment file. Later on, there was like an insecure file copy in post-install script or insecure hard link creation on post-install script. Actually, I found those as well. And then we have mitigation. He's a guy from China, and he has a ton of CVs concerning this daemon, but he's mainly exploiting the daemon or the framework the daemon is using. So he's more focused on the inner workings of the daemon and not on like external packages. So the software catalog, how do we get packages that we want to exploit? So we can go to developerapple.com, download all, and you get some packages from there, but it's very limited. There is also supportapple.com from where you can download other packages for your operating system. But again, these are very limited. There are not a whole lot of packages. So are there more? Yes. So I read an article last March, which was written by Michael Cowell, and he said that he analyzed the entire SU catalog. And I was like, SU catalog, what's that? So turns out there is, that's a software update catalog that you can download, and it will list all of the packages you can get from Apple and potentially install. Now, each macOS version has their own catalog listing all the products that's supported by the OS. The URL looks like this. It says index, and they list all the macOS version back to Leopard, which is like 15 years ago. I'm not sure, but that's like really old. OS version. And this catalog is basically a huge XML file. It's a property list file. Apple is using property list files for everything. It's an XML file. So this is how it looks. It has a list of products. Each product has a key. There is a metadata URL, but that's not interesting. And then they list packages. The package has a size and the URL, basically, and the post date, which will say when this package was posted. So actually, many Mac sysadmins monitor this software catalog and notify users that, hey, there is a new version of this software, or there is a new software that you can install. So this is a known thing. So the challenge was, like, actually reading this article kicked off my entire research. And I was like, okay, Michael Cowell, and he said that he analyzed the entire software catalog. So he did the same work as I did, and he found quite a few vulnerabilities there. But I was like, still like, okay, but what if there are still vulnerabilities, although it has been looked into? And there is a chance for that. Like, I often find vulnerabilities in locations that I already thought that I exhausted. And there is a ton of packages, like really a lot. And I was like, okay, for this scale, like if I download all of the packages, there is no way I will do it by hand, so I need to automate it. But I do suck at automation. Like, I know my limits, and automating stuff is my weakness. So I was like, okay, let's do ChatGPT. I was skeptical in AI, like I never used it before, really. But essentially, I was more lazy than skeptical. So I was like, okay, let's see if ChatGPT can help me to automate all the things. And let's see what it can do. So step 0, get all the URLs for all the software catalogs, because I want to download everything. Turned out there is a GitHub page which keeps track of all of these URLs. And I was like, okay, ChatGPT, can you grab me this web page and basically parse the content and get all the software catalogs? And eventually, in like 2-3 iterations, it did it. So I was like, okay, we will get somewhere. The next one was to get all of the packages. But before I downloaded them, I wanted to be sure that I have enough space. It turned out that it's like 1.3 terabytes of data to download. Luckily, I have a fast internet and a large hard drive. And that was like 10,000 packages to download. So it did it. It required some iterations, but it did all of that. And actually, it knew how the software catalog looks. Although at the end, I had to tell it what's the XML structure and what to look for. But it went pretty easy. So now I got all the packages, and I had to basically start removing packages which are not interesting, because there is no way that I will look in 10,000 packages. And also there is, like, I knew a few typical vulnerabilities in these scripts, but it doesn't cover everything. So I wanted to look every potential vulnerable package. But again, there is no way you will do this for 10,000. So I was like, because I'm looking for script issues, like embedded pre- or post-install scripts, I was like, okay, let's remove all the packages which do not contain any script. That was like a short shell script which did it. Step 2, delete all the unsupported packages. So some older version of packages actually wrote files to /system, which is now not just zip protected, but it's not even mounted. So there is a snapshot taken from the system partition, and the snapshot is mounted. And the snapshot is not writable by design, but it's also read-only mounted. And because there is no way you will modify the system partition, the installer will just say, this is not supported and will not run it. So again, those packages were not interesting. Step 4, some packages contained only a few default pre or post install scripts, which basically only did some logging and so on. And those were not vulnerable. So I was like, okay, let's get rid of all of those packages which contain the default pre and post install scripts. Then there were a few other files in the software catalog, a few plist files, a few tar files, zip files. These are not packages, or if you decompress them, they contain some very old type of package, which was not interesting for this research. I was like, okay, let's delete all of these files. At step 6, we are getting more into the manual analysis. So there was a bunch of printer packages which contained PPD files, which are post-script printer descriptions. And they contained, I think, one script related to PPD files, and it didn't contain any vulnerabilities. So I was like, okay, let's delete all of these printer installers that contain only this script and PPD packages. So eventually, it got down to around 300 to 400 packages, which I couldn't filter out more. And I actually analyzed them one by one. There were a few duplicates, so it wasn't. I didn't actually look at like 300 or 400, maybe half of it. But it's still a lot to go through. But that was a manageable size at that stage. So with that, let's see what vulnerabilities I found. First one, it was in the iDVD extra content package. And that allowed me to fully bypass zip, basically write to any zip protected location. And again, our target is this TCC plist configuration file. So this installer contained two scripts. One was a pre-install script. It was now move teams aside, and there was a post-install script, now copy teams back. Essentially what it did, if you already had like iDVD teams, it backed them up, installed a new version, and restored all the teams. Now the problem with this script was that it operated in a user controllable location. And user, in these cases, we always mean root user. But again, don't forget, root doesn't equal God mode on macOS. So even if we are root, we are still looking for more privileges. And all these teams were in the library application support iDVD folder, which is accessible for root. So this was the script. I hope it's visible properly. So there are some it's a Perl script, I think, and it contained basically the left one is the backup part, where it constructs the backup folder, and there is a rename at the very end where it backups the teams folder to the move aside folder. The right one is the post-install script, and at the very end, there is a ditto command, which is a copy, basically. And it says, OK, copy the files from the move aside folder to the teams folder. Now, the vulnerability is that we can subvert this ditto command. First, we can replace the teams folder with a symbolic link pointing to our target of interest. And on the move aside folder, we can put our file that we want to drop. And when the ditto copy happens, it will copy my file to the location my symlink points. And that's it. So basically, I put my hello application list plist into the move aside folder and replace the folder with the symlink. And at the end of the installation, my file was copied to the right place. So this is how it looks. These are the privacy settings, and showing that my terminal doesn't have access to only to download to the downloads folder, and it doesn't have full disk access rights. So if I try to list files from the desktop, you can see that it's not permitted, although we are root in this case. So we run the exploit. The installation is done, and we get access to the desktop, although there is nothing right there. And basically, it says that the symbolic was created, and that's our updated plist file. Thanks. The next one was actually in a printer installer, and it was only like a file overwrite vulnerability, so it's like more like a denial of service. The script was very simple. It basically says the temp file is in the temp folder called gpay.co canon macops installer pskill, whatever. The temp folder is accessible for everyone. You can basically create a symbolic link in this place and redirect the log right. Now, you don't have control over the content of what's being written into this file, but you can potentially damage important files. So we can, and Xprotect is one of them, which is C protected, but not part of the core system. So what we can do is overwrite Xprotect, which is the built-in malware scanner of macOS. And if you overwrite Xprotect, then basically you disable the security feature on macOS, which is nice. But still, it's still only a denial of service. Next one, recovery HD update. It was also like a full TCC bypass or SIP bypass. They have a replace recovery script in the installation, which again was working in the /temp directory, which is accessible for everyone. Now, what happens here, the installer drops a DMG file. The DMG file is a disk image, like an ISO, and it will also mount the DMG file somewhere under the temp directory. So we can see that it calls pkgutil to extract a package into the temp dir, and once that's done, it will call HDIutil to mount the DMG file, with the mount point also pointing to the temp directory. So what we can do is, once the package is dropped or expanded, like extracted, we can replace the DMG file with our DMG. So we control that one. And for the mount point, we can place a symbolic link there and redirect the mount to our location of choice. So, and basically mount the DMG over a directory which contains a TCC database, and drop a new database with our arbitrary content. So because this was like a race condition, I did the following. I detected in my exploit if the Perl script was running. I stopped the Perl process, so I can swap the DMG file and also replace the folder with a symbolic link, get Perl to continue. And once I detected that the mount happened, I killed the Perl process because at the very end of this script, it unmounted the DMG file, and I didn't want that to happen, so I just killed the process. And then at the very end, restart tccd, so the new database is read and takes over. So we again see privileges for terminal at right. We can see that it only has access to downloads at this stage. And now it's refreshed, and you have access to everything. I mean, I could add more, but this is just for the demo. Okay. So another one, it's also zip bypass. Now, it was interesting because when I found this, so these previous 3 vulnerabilities were the new one I reported to Apple. This one was already fixed, but I don't know the CV number for that. And there is definitely not, I haven't found any public talk, blog post, whatever, that actually describes or writes about this vulnerability. So it was fixed at one point, but I don't know who found it and who reported it originally, but I'm definitely not the first one. So again, this contained an alert all install script, and it used an environment variable, the user environment variable, in the sudo-u user alert all target. Now the alert all is set there, and interestingly, what we can do when we call the installation, we can transfer this environment variable, the user, to the installation process. So, and by doing that, I can inject basically a command there. So the user can be anything. So I can do a command injection at that line. So that's how you run the installer. It says user equals something, root, and then you specify the script file, which is the script you want to run. And the shell will interpret this and run it. So actually, this was the entire exploit. The exploit dropped a script file. The script file overwrote the plist we are always working on, and then just said user equals root script file and install the package. And basically, we injected the command into the installer. So we have a secret on the desktop, again showing that the plist is empty right now. And yeah, I recorded that I cannot type, or I don't know where I am, but yeah, I cannot list the desktop. Normally, we run the installer. We gave ourselves full disk access. Again, the plist, and then we can just list the desktop. And the last one, again, a full zip bypass. Another vulnerability which was already fixed. And again, I don't know who is the first founder here. But what the script did is copied a PEX file, which is a compressed file, and extracted it. And we control everything here. So we can drop our own PEX file because it's a user controllable location, and we can also control the destination. So we can extract the file to somewhere. So again, we are doing the same trick. you're probably bored by this now. So we are doing it again and again. This is actually, I'm showing, running this on macOS Ventura because it was fixed long time ago. But yeah, the same story. So how Apple fixed these? The problem that these are signed packages, and because they are, if they are signed and validly signed, then system installed will install them. So let's say you fix the package and you released the next version of the same software. I can still use the old package because you cannot revoke that certificate that signed all of the packages. So like that would be a nightmare. It would break everything for everyone who uses these packages. So you can't revoke the certificate. And although you fix the package in the next version, I can still take the old package and use that for exploitation. It's like a forever day, because even if you fix the package, I can use the old one with like downgrading to achieve this. So yes, you fix the package, but you cannot fix all these on the package level. You have to mitigate it somehow at the operating system level. So what they did, and actually this is quite a recent thing, so they started doing this a year or 2 years ago, is they added a few configuration files to the package kit framework, which is the framework used by the system install process. And they have 3 different configuration files. The first one which came was the install script action. And it defined that if I have this script in the package, and they specifically stated the name of the script or the path of the script inside the package, so that's the relative path, and they also listed the package identifier. They said drop zip, which means drop the privilege of the installer from accessing zip protected location. So it's like downgrading myself before I start the installation. So I cannot exploit this anymore because the daemon will not have the proper privileges. So I can no longer exploit this. And this works. The other thing they did, it's called install script mutations. And they did it for only a single package until today. And actually, it's a package I reported a few years ago. What they did here is like find this script, and again, they specify the script name and the package, I think, or find this script, and they put a regex in that replace this content with this content. So basically, they replace the script on the fly before it's being executed. So they essentially apply a hot patch to the script before it's being run. Again, it's only used for one script. But eventually, these two, they realized that it's too much work, and we can just, all these packages don't require zip bypass privileges, so we can just drop zip entirely. And the latest addition is the install script tries. And it just said, if this is the package, drop zip. We don't care about the script, we don't care about everything, just drop zip. And basically, probably all of these packages had a vulnerability at one point. So, yeah. So now, even if you use any old version of these packages, you can no longer run these exploits because the installer will not have the sufficient privileges. And that's it. Thank you.
Thank you very much. Really interesting talk. Any questions? Surely there needs to be questions. Yep, we have one over there. Do we have a runner in place? Yes, we do. Let's see.
Hello. Yeah. Really nice talk. I just had a question. I'm a bit of a macOS noob, so maybe this is pretty obvious. But in one of the exploits where you had the race condition, you could pause and then kill the process as root. But so that process is running on a higher privilege, but you're still able to stop it and kill it? How, like, is that not a security boundary?
Yeah, so the process is running as root, although it has some strong entitlements. Strangely, I can still stop, resume any process if you are root.
Yeah.
Probably at that level, stopping a process or resuming, that's only the user privileges that count. Because you don't really gain anything other than more like a denial of service attack, but you cannot utilize that piece of daemon or software to do anything. You still cannot inject code or do anything.
Yeah. Okay.
So I guess they allow it.
Anyone else? Surely there is questions. No?
I know it's lunchtime and I'm between your food and your lunch, and that's not a good place to be.
So, any final questions for Csaba? No? Okay, don't go anywhere. Thank you, Csaba.
Thank you.